Assalamu alaikum. Hello everyone. Today I will walk you through design and simulation of a gold bowtie nano antenna in CST Studio. So what is the purpose of this antenna? The bowtie nano antenna is designed to capture and concentrate the light energy in an optical frequency range, basically in the terahertz range. Its sharp triangular tips concentrate the light because it's create a strong localized electric field, which makes it is useful for application like energy harvesting, nano sensing, optical sensing, and nano communication systems. Now let's jump into CST to design our antenna. So first of all, we are going to create a new template. From here we are taking microwaves and RF optical and antenna. So and this is a patch type antenna, so we are going for this. So here it is, we are taking time domain because our antenna operates in the optical range, which is terahertz frequency, and the time domain solver is efficient for broadband simulations. So let's go with time domain. These units we are using in the whole design. So our all dimensions are in nanometer because this antenna is going to be very small, and the frequency is in terahertz because obviously we are using nano antenna. So let's go. And we are taking the minimum and maximum frequency to from 300 to 450 terahertz because this converts the visible and near infrared spectrum where plasmonic nanoantennas are most active. By covering a broadband, we make sure the antenna's resonance frequency is captured. Okay, and also we want to monitor all kind of results like electric field, H field, power flow, and power loss. So let's go. And this is the overall summary of what we have done yet. So let's go. Okay. Now CST Studio has brought us in its main designing window. So let's start designing. So first of all, we are going to create a substrate. We're going to create a substrate made of glycerin. We would like to use glass, but as it is a CST learning edition of this software, CST won't allow us using glass. So let's go with the glycerins. So to make the substrate, let's go to the modeling. Here we are. Let's name it substrate. And X min we are giving 200 nanometer. X max is 200 nanometer. So it is going same for y axis, and for z axis we are using 100 nanometer. Okay. And in material, as we said, we are going to use glycerin. Okay, so here is our substrate visible. Nice. Now we will create the arms of the bowtie. So let's go with polygon. Let's name it bowtie arm 1. Let's keep the parameters 10, 0, 130, minus 60, 130, 60, and again to 10, 0. Okay. So this is our first term. So let's go draw the second term. Bowtie arm 2. For x we are having minus 10, 0, minus 130, minus 60, minus 130, 60, and again minus 10, 0. Okay, so here now our two bowties polygonic structure is visible. So we would like to make it, this is actually 2D bowtie. Now we are going to make it 3D bowtie, a working bowtie, and we are using the material in bowtie is gold. So next we are going to extrude the bowtie and name it bowtie 1, bowtie arm 1. We are going to make the arm in thickness is almost 30 nanometer, so minus 15 to 15. and we are not going to add any twist or taper, because the more sharp the edges are, the more fields are concentrating, more light are concentrating in this area. So let's start. For again, we are going to use this 130 minus 60, 130, 60, and 10, 0. Okay. So, and in material we are going to use gold. Where is gold? Gold. Okay. So here you can see first arm, and we are using it for the second arm also. Both die 2, arm 2, same thickness, minus 15 to 15, no twist and tapers, minus 10, 0, minus 130, 60, minus 130, 60, minus 10, 0. Okay, so we have our structure almost complete. Now we are going to add the excitation in this between this 20 nanometer gap. So let's go to a discrete board, and we are going to see the S parameter value. So impedance is 50 ohm is okay, and radius we are keeping 2 nanometers, and the coordinates we are going to add is 10, and this is minus 10. Okay, so there our port is inserted in the antenna. So now let's take our we have to set the field monitors. So let's set the field monitors is okay, and this is what we want. This is fine, and this is fine, and on the other side we want to see the boundaries is if they're open. Yes, they're all open. So now we are going to simulate this. Let's start the simulation. Second. Well, we need to decrease the mesh size, so let's go for the mesh. We're going to come here, modeling. Where is the mesh? Here is the mesh properties, cells per watt. So okay, let's keep it 7. It's 10, and also this is 10. Okay, let's apply it. Now let's try to simulate it again. Let's wait a bit. Let's wait a bit. It may take some while. From this simulation we are going to see the results like S parameter, electric fields, and the losses of golds and etc. we have used. So yes, we can see it's successfully simulated. So let's go check the S parameters. It may take some while. From this simulation we are going to see, yes, this is the S parameter. So we can see the S parameter here. Here is the E field, electric field. This is for 375 terahertz, and here you can see the H field also, and obviously the far fields. Here you can see the far fields. This is for 375. This is for minimum 300 terahertz frequency, and this is 450 terahertz frequency. So now we are going to discuss the results. Now let's start with the results of our antenna. I mean to say the S parameters, E field, far field, etc. So let's start with S parameters. So in S parameter graph, we can see at 375 there is a noticeable dip indicating that the antenna is resonating and capturing part of the incident energy. At 430 terahertz, the dip reaches almost minus 40 dB, which means that nearly all incoming energy is coupled into the antenna with minimal reflection. This is the strongest resonance point, making the antenna highly effective for energy harvesting. So when this is the S parameter analyzing. Now let's go with the E field, and the electric field plots confirm this behavior at 300 terahertz. At 300 terahertz, you can see some values here. At 300 terahertz, the fields are weak and spread out, showing no resonance. And 375 terahertz, a strong hotspot forms in the 20 nanometer gap, providing efficient near field enhancement. And at 450, the fields are also strongly localized here, consistent with the tip S11 S parameter tip S11 tip. Now when we go for the far field this is the far field visualization. So we can see the far field radiation patterns also change with the frequency. At 300 terahertz, the radiation is weak and scattered. At 375, the antenna shows a dipole-like radiation. Here you can see this is the two pole, one here and another here, dipole-like radiation pattern with a clear main lobe. Main lobe is, we are considering this is the main lobe, and along the antenna is confirming efficient radiation and resonance. At 450, the dipole-like radiation remains strong and efficiency is higher, matching the strongest resonance from the S11 curve. And if we summarize this, the Bowtie Nanoantenna shows two resonance mode: 375 terahertz, strong near field hotspot in the gap, and at 450 terahertz, very efficient energy coupling, like it's like minus 40 dB in S11D. Together, this results confirms that the Bowtie Nanoantenna can effectively capture, concentrate, and radiate optical energy, making it highly suitable for energy harvesting.